Hey guys, welcome back. Welcome back to my channel. This one it's sections 4.2. Well, you might be wondering, it's showing that 3.2 here because that's a different textbook that I use for pre-cal. So this one's supposed to be 4.2 from the James Stewart. So it's the logarithmic functions and the graphs. So define that for x greater than 0. So a is greater than 0 and a does not equals 1. So y equals log base a of x if and only if x equals a to the power of y. So this one is just like different way to rewrite it, exponential form, okay, which is considered x equals a to the power of y. And then this one can be written as the logarithmic form. So y equals log base a of x. Okay, so the way to do that, so we still keep the same base, a, and then for the power and the variable, we just need to swap them. So the power and the result, we just need to swap them. So like this one here, this one is written as 27 to the power of 1/3, so that equals 3. Well, you might be wondering, it's like cube root of 27. What's cube root of 27? It's 3, right? But in the log form, this one is written as log base 27 of 3, so that equals 1/3. Again, the base, we just keep the exact same number for the base. And then for the exponent and the result, we just want to swap those two positions. And also like this one here, log base b, and then of a, so what is that equal to? The power 14. So convert from exponential form to logarithmic form, and that's what I just did here. And now what about going backward from log form to exponential form? So start with the base. What's the base here? 2. Power 3. And what's the result? 8. Does that make sense? 2 to the power of 3. 2 times 2 times 2 times 2. Which is what? 8. And then this one right here. So m to the power of q, what is that equal to? N. Okay, just like that. So it's pretty basic. And now, what about for something like this? The way to simplify it. And anytime they want to simplify it, if you're not quite sure what that is, you can always rewrite it with x. So basically what this one is showing that here is showing that cube root of 5. Okay, so that one is a cube root of 5 to the power of x. So what is that equal to? It's 125. Okay, so cube root of 5, so that means 5 to the power of 1/3 x. So that equals 5 to the power of 3. So in other words, that 1/3 x equals 3. So what's the value of x? 9. Okay, so that's one way of doing it. Another way you can do it is using that same log base. So anytime that we see the same log base, like log base of b, so this one is always 1. It's the same thing as b to the power of log base b. It's always 1. Okay, why is that? Because b to the first power, it's always b. So another way you can do it, this one can be written as log base. So 5 to the power of 1/3. And then this one, 125, so 5 to the power of 3. Okay, so now the thing is that if you try to use that the same log base, does that apply for this case here? So it looks like it doesn't apply for this kind of situation, because we need to come up with the exact same base, the b and the b. But this one here, we cannot do that. Okay, but what about for the next one? Can we come up with the same log base? So this one, you try to do it with the first technique, then that'd be kind of difficult because you need to set it equal to x. Again, if the base is not shown, it's always 10 for log. So what's log base 2 of 1024? So 1024 can be written as 2 to the power of 10. So what we found here, it's log base 2 of 2. Using that the property, it's the same log base, it's 1. So it's log base 10 of 1 to the power, well, it's just 1 times 10, then that'd be 10. And then log base 10 of 10, which is 1. And that's the final result. Okay, so it's kind of interesting with a problem like this. And one thing that we notice, log functions, exponential functions, they're just considered the inverses of each other. Okay, so you try to find the inverse, you'll get that it's an exponential function. Okay, so x equals y, the line of symmetry. So here's f of x, the log function, and here's the inverse of f of x. In order to show that they're inverses, so here's what we can do. So set y equals log base a x. And then the way to find the inverse, we swap the variable. So x equals log base a y. In order to solve for y, this one we want to convert it back to the exponential form. So in other words, a is the base to the power of x. So what is that equal to? Y. And then y is already used for the original function, so we want to put it as an inverse notation. And that's what we got. And one thing that we notice for the compositions, so let's say that f of inverse of f of x. So this one is always the same as x. Eventually, if you try to simplify it, plugging that the inner functions to the outer function. Well, because that those two functions, they're inverses of each other. So it doesn't matter which way that you started first. You started with either inverse of f of x or you started with f of x first. So once you plug it back to the inverse, the final result, you always end up with x. If that's the case, so that means those two functions must be the inverse functions of each other. Okay, so this one, the same thing happened for that log base e x. So that equals natural log of x. So the inverse of that, the exponential function, e to the power of x. Okay, so let's try that. So y equals natural log of x. Find the inverse. We swap the variable. And then take the base e on both sides. So we got e to the power of x. So that equals inverse of f of x. Keep that in mind. E to the power of natural log, it's 1. It's just the same as natural log of e. So 1 times y, which is y. Inverse of f of x. So using the properties that for the exponent, so we can simplify the following. So log 100 of 2x. Again, so this one is written as log base 10 of 10 squared to the power of 2x. So basically what's left here is just what? 2 times 2x, so 4x. Natural log of e to the power of 2x, just 2x. And then e to the power of 5 minus, so that means it's a quotient, e to the power of 3 times natural log of 2. So this one, basically we can simplify it a little bit. So e to the power of 3 to the natural log of 2. It's just like e to the power of natural log of 2 to the power of 3. Okay, so we just consider 8. So this one can be written as e to the power of 5 over 8. Because that's like 2 to the power of 3. Power to another power. And this one, just split it using the property. Well, should go over the property as well. So again, anytime they see like natural log of x over y, it's just like natural log of x minus natural log of y, quotient to difference, product, x times y, natural log of x plus natural log of y. And then if you see the power like this, so that means you can always bring down the power to the front, like that. So this one is written as natural log of 1 minus natural log of e to the power of 1/2. So what's natural log of 1? Well, another property, so that's 0. So 0 minus natural log of e, 1 times 1/2, 1/2. So it's negative 1/2 for this one right here. So natural log of 1, that's always 0. And then what about a log base 2? So this one is written as 2 to the power of 3 times log base 2 of 1 over 16. Again, coefficient to power. So this one can be written as 2 to the power of log base 2, 1 over 16 to the power of 3. So eventually it's 1 over 16 to the power of 3. So it's 1 over 16 to the power of 3 times 16 3 consecutive time. So this one is something you want to try. So it's quite similar to what we did. So it's the same log base 2. So another thing that I would like to go over here, it's about finding the domain, the range of the log function, and also making a graph. So if you guys do recognize what we did in Algebra 2, so y equals a log base b of x minus h plus k, the transformational form. So what we found here, a is 1, so the base is 2. And for those you might be wondering, h is not given that kind of obviously. Okay, so this one, so what we can do, we can set that 3x minus 1 equals 0, and then solve for x. Whatever the value of x that you find out for this 0, then that will be considered the value of h. So 3x equals 1, so that means x equals 1/3. So h is 1/3. And then the value of k, it's 1. So back to the exponential function, the value of k, it's always the horizontal asymptote, but log is the inverse of exponential function. So that means the value of h would be the vertical asymptote. So right here, 1/3, then that'd be the VA. Okay, so here's 1/3. Another thing that we can find out, so the points, xy table. Okay, so can we find the y-intercept for this? So plug in 0. Well, let's see, this one looks like it's impossible to find the well, it's possible to find the y-intercept. Another thing you might be using is that the property, so log base 2 of 2, it's always 1. So in order to satisfy the quantity as 1 here, well, in order to satisfy the quantity as 2 here, so 3x minus 1, so set that equal to 2. So we got 3x equals 3, so that means x equals 1. So log base 2 of 1, well, log base 2 of 2, then that's 1. So 1 plus 1, then that'd be 2. So 1 comma 2. And now what else can we apply for this quantity here? So another thing that we notice, log base 2 of, so log base 2 of 1, so that equals 0. So we can set that quantity equals 1. So that means 3x equals 0. No, 3x equals 2. So that means x equals 2/3. So when x equals 2/3, so this one is 2 minus 1, which is 1. So log base 2 of 1 is 0. Because 2 to the power of 0, that's 1. So 0 plus 1, then that'd be 1. So 2/3, and then comma 1. Okay, so it's a log function. So it's going this way. And then the natural log 1, so we can apply that xy table. Again, the value of h is not shown, so that means the VA, this one will be 0. And then xy table using 1, the value of e. So what's natural log of 1? 0. Natural log of e, then that'd be 1. So 1 comma 0. And then e, 2.7 comma 1. Okay, so like this. So one's the log function, the other one's a logarithmic, the natural log function. And then the rest of those, they're quite similar, but here's the one I would like to show you. So for natural log of absolute value of x, so you might be wondering, h is 0? It is. But keep that in mind, h this time is what? With the absolute value. So that means we can plug in negative number, positive number. For the positive, so it's going this way. And then for the negative, so natural log of negative x. With the negative right next to the variable, that means reflect it over the y-axis. So it's going this way. So kind of like an upside down volcano. Okay, so now the rest of this is about solving. So in order to solve for the exponential functions, so let's see, we need to come up with the base, the common base, or perhaps we probably have to factor something out first. Well, let's do it this way. So the separated constant has nothing to do with the exponential functions. So what we can do, we can combine the like terms. So 6 times 2 to the power of negative 2x plus 2 to the power of negative x. But this one, well, this one has an exponent. So what we can do, we can set up the replacement. So let's say y equals 2 to the power of negative x. And the purpose of doing that, we just want to put in the replacement. So it's easier to find out what kind of equation that is, because this one is kind of like a mix of exponential and quadratic. So what we got here is 6 times y squared, because that 2 right there, just like the quadratic, the power 2. So y squared plus y minus 1, so that equals 0. So what we can do first, we can solve for y, and then once we solve for y, we can then substitute, and then we can solve for x. So let's put it right here. So 6y squared plus y minus 1 equals 0. Is this factorable? Yes. So 3y minus 1, and then 2y plus 1. So what we can do, so set it equal to 0 separately. So we got 3y minus 1 equals 0. 2y plus 1 equals 0. So y equals 1/3. And then y, right here, it's negative 1/2. So for y, what is it? It's 2 to the power of negative x equals 1/3. And then the other one, 2 to the power of negative x equals negative 1/2. And for those you might be wondering, is that possible to have a negative result for 2 to the power of negative x? Because this one is considered the exponential decay functions. And y, it's always, the range for this one is always greater than 0. So there's no solution for this part. Again, 2 to the power of negative x. So that means it's like exponential decay functions going this way. The y value, it's always getting close to 0, but it's never less than 0. So that's why there's no solution for this. But what about for 2 to the power of negative x equals 1/3? So in other words, this one is showing that it's like 1/2 to the power of x equals 1/3. So the way to solve for x, we're using logarithmic model. So it's log base 1/2. Okay, let me just rewrite it. So for log 1/2, base 1/2, 1/3, then that equals x. So what this means is that it's log of 1/3 divided by log of 1/2. And then that'll be the value of x. So that one is going to be a very small number. Okay, so you can try the rest of this to find out the value of x. So in order to bring all the x terms together, well, this one is a little bit difficult because that they don't have the exact same base. So what we can do, we can take either the log on both sides, or we can take the natural log on both sides. And using the properties of logarithm, bring down the power. So we got x natural log of 2, and then 1 minus x natural log of 3. And then from here, we want to distribute. And try to bring the x term together. So x natural log of 2 plus x natural log of 3. So that equals natural log of 3. Take out the greatest common factor, x. So we got natural log of 2 plus natural log of 3. So that equals natural log of 3. So finally, x, divide both sides by natural log of 2 plus natural log of 3. Okay, like that. And now, what about for c? A lot of people might be saying that, well, we can cancel out the x, we can cancel out the e to the power of x on both sides. If you try to do that, you can only find out one solution, and that's just x equals 4. And that's not the correct way to do it. Because anytime that you try to cancel something out, that means you cancel out some of the solution as well. Okay? So non-linear, you cannot do that. So you always want to bring everything together to one side, if that's considered non-linear. So according to the structure, this one, it's a non-linear equation. Besides being the exponential, it's also considered what? Quadratic. So x squared e to the power of x minus 4x e to the power of x. So set equal to 0. So now what we can do, instead of canceling out that e to the power x, so what we can do, we can take out the greatest common factor. So x e to the power of x. So what's left here, it's x minus 4. That's what I mentioned before. If you just cancel them out, you only find one solution. But besides finding one solution right now, what else can we do? We can find out the rest of the solution right here. So x could be 0 as well. And e to the power of x, can that one be 0? This one cannot be 0, because that the value of k, it's the asymptote. 0 is the asymptote, so this one there's no solution. So it's only 4 and 0. Okay, so the rest of this is just like critical thinking, so you probably want to try that. So for a and 9, okay, so number 9 is quite interesting. Also number 8 is quite interesting. So find the product. So that one is just basically distribute. Okay, so multiply things out, you'll see what happens. So it looks like that one, it's like a perfect cube. No, just it's a difference of 2 cubes. And this one right here, so solve for the equations. So you want to solve for C. So try to condense all those elements together if that's possible, and then solve for C. And then this one here, so you want to convert that back to the exponential form first, probably. And then from the exponential form, you want to solve for the quadratic. Okay, so the quadratic, so that means you have to factor a little bit. So for a and 9, so those are the one that I would like to think about it. Okay, so thank you for watching the video today. So I'll see you guys next time. And don't forget to subscribe to the channel. See you later.